Hi, I'm Alex, and also on the team is Caroline and Frankie. And Caroline can do the introduction.
Okay, sure. So, as you can see in the poster, in the introduction section, about 1.2 billion people still don't have access to electricity in their homes. And specifically in this map, we can see that the places that are still greatly lacking in electricity are pretty unevenly distributed. But as I'm sure we're all aware, access to electricity is becoming increasingly critical, especially for promoting economic development and improving living conditions. I think it's also been shown that electricity access is correlated with improvements in income, education, maternal mortality, and gender equality. So this sort of leads us to the motivations of the overarching project that our Data Plus team is a part of, which is how we can contribute to improving energy access for areas that are currently lacking. So one of the first steps in starting this process of improving energy access is acquiring comprehensive data on the existing energy infrastructure in a region. So this includes things like the type of infrastructure, the location, things like that, so that energy developers and policymakers can then strategically deploy energy resources. So this information is key for helping them make decisions about where they should prioritize development and whether they should use like grid extension, micro or mini grid development, or off-grid options. Um, and this is sort of also where the problem lies, because oftentimes this information on that's used for expanding energy accessibility is scarce or low quality. And one solution to this issue that people are beginning to explore is to use machine learning to automate the process of mapping energy infrastructure with satellite imagery. So using deep learning, we can feed a satellite image of a region into a model and make predictions about that region's characteristics and contents. So specifically, the idea is to use object detection. So essentially, after training a machine learning model on data sets consisting of satellite imagery, in which the objects we are interested in are labeled, which in our case is wind turbines, as you can see. We are then able to input new images into the model that it has never seen before, and ideally it'll analyze the image and output predictions for where exactly those wind turbines are located. And this seems like a pretty promising solution, but there are two key challenges that arise. The first is that, like I touched on, training the model requires an immense amount of data, which is a problem because many types of energy infrastructure, like wind turbines, are pretty rare. So it's hard to find satellite imagery with wind turbines already labeled, and the alternative of manually collecting and labeling satellite imagery by hand is pretty expensive. And the second problem is that these models aren't super capable of generalizing well yet. So that means that if we train the model on a bunch of images, say from one specific region, that look a certain way, then when we try and apply this model on a different region that has a different look, say like if the region we trained on was like grassland and then the region we try and apply it on is desert, the model will not do as well because it's not as familiar with those kinds of geographies. So therefore, our proposed solution to addressing those two problems is to introduce synthetic images to our training data set in order to supplement the real satellite imagery. So specifically, what our project has been working on this summer is using an image blending technique, which I think Frankie and Alex will get into, to blend images of satellite images that already had wind turbines with other satellite images that currently or originally have no wind turbines, to create new images to supplement our training data set.
All right, yeah, I can take it from here and go into a bit more of our methodology. And so in the past or last year's Bass Connections team, their solution was to essentially make 3D models of different energy infrastructures, and then they would actually like place it in these new locations that we're trying to get a mapping for. But our strategy was this image blending that Caroline was talking about. And so getting into that more, with this image blending, we can take as opposed to the 3D models that the last team used, we can use real wind turbines, real plants, real transmission towers, and then we can just blend them into a different background. And that will allow the model to be used to seeing an energy infrastructure in these different terrains, so that when we try to get this mapping, it will be used to a diverse array of these kind of energy infrastructures. So if you look at this picture, it's kind of small on the poster. It's getting into kind of how our data generation pipeline worked. And so at first, we kind of sample these real wind turbines. So, it doesn't take that many, but we can go through our real collected data, our database of real images, and just take some wind turbines. The second part of the process is that we put these in these randomized like sizes, locations, and rotations. And the point of that is that not only are we trying to put the wind turbines or in a new terrain that we're going to be testing on, but we're also trying to get the energy infrastructure detection model to be used to seeing wind turbines at different angles, in different perspectives, different sizes, because all in all, like, it needs to be able to detect it in all in all, like, when you test, you don't know exactly the angle of the imagery will be or the size of the energy infrastructure, so it needs to be able to detect it for all these different features. Finally, once we have this kind of canvas with all these different wind turbines on it, we blend that with a destination image. So if you see on the right in that under blend image, there's kind of this grassy image. There's no wind turbines in it. And then so all the way, so up, so under blend image, there's kind of this blank, there's a destination image. And then all the way on the right, it has the wind turbines in the exact locations, rotations, and sizes that that were on the canvas, but it's now in this new destination image. And so now if you're like an object detection model, you're seeing these wind turbines that maybe you only saw in a deserty region. Now you're seeing it in a grassy region, and you're able to understand what it would look like in that context. And so using this image blending is all about trying to, put these like wind turbines and other energy infrastructures in new context, so that when the object detection model runs into this energy infrastructure in this context, it will be able to detect it. So going a little bit more into that, because image blending is kind of like a very vague term. So we use something called a generative adversarial network to do this image blending. And that's even more of a mouthful. But it's basically a model. So the idea is that it's going to generate new images based on a set of training data. And so in training this like generative adversarial network, I'll call it a GAN for short. It's basically blending the images multiple times, and there's another model that tries to detect whether the image is real or fake. And so it keeps getting that output of whether it's real and fake, and tries to keep making the blending better and better until the other model can tell if it's real or fake, is kind of the idea behind this generative adversarial network, or a GAN. And so that allows for us to generate more realistic imagery. So it's able to, in that output, it can kind of combine different contexts. Maybe if you zoom in on the output, sorry.
You're good.
So if you zoom in on the output, it's taking images from a deserty region, a foresty region, grassy regions, and it has to combine all of these into one grassy region. And so you can see that, on the bottom of the output image, it's putting kind of like a green hue to like the desert in order to make to blend that more effectively, because a deserty patch in the middle of grass is pretty unrealistic. whereas others, it kind of, with the grassy region up top, it kind of just smoothly blends it out. So it's able to kind of learn what is more realistic and not, and then lead to us creating these more realistic output images. And the idea behind that is, if we can, create these synthetic images and them look realistic, then that makes it almost as good as just having more real training images. And all in all, this whole thing is about, we need thousands of images to get optimal performance on this energy infrastructure detection model. And if we're able to generate synthetic imagery that's almost as good as real imagery, then we can easily hit those data thresholds without having to worry about the time and money cost that goes with getting such large data sets. And so it's a quick and cost-effective solution to exactly what we're going for. It takes very little manual stuff other than just, sampling the windmills. And then the rest of the mapping in terms of, randomizing the location, the rotation, the size of the windmills, and the actual blending is going to happen automatically and very quickly. The model is able to blend an image in 7 seconds, which is way better than you can do in like Photoshop. So it's a very kind of quick solution, which is exactly what we need for our data set. So I'll let Alex go in more into the actual experimental setup that we used once we generated this synthetic data set.
Yeah, so our experimental setup was to see if our generated synthetic imagery was actually able to do the trick. Traditionally, object detection models for satellite imagery doesn't perform well cross-domain. So what that means is you can take a look at this map in the middle of the experimental setup and result column, and you can see the Eastern Midwest region or domain, which we refer later to as EM, and the Northeast region or domain, which we refer later to as NE. And you can see the differences in them. So NE has more trees, is more dense, and perhaps has more hills, and EM is flatter, grassier land that looks more groomed. So object detection models traditionally perform worse when they're trained on one domain and have to classify images from another domain, which we refer to as cross-domain. So in order to test the efficacy of our synthetic imagery, we set up within domain and cross-domain experiments. And let me zoom in on this image here. So for a within domain experiment, the training data is from the domain that you validate on. And for a cross-domain experiment, the training data is from a different domain, and the validation data set is from a different domain as well. So that's where the cross comes from. And we are trying to see if by adding synthetic imagery, we can boost this cross-domain or even the within domain accuracy. And our measure of accuracy is a measure called average precision, or AP, which measures the area under the PR curve, which is a precision recall curve. And this is a standard measurement that's used across the object detection field. And it's a good general marker when also used with other accuracy measures. As for our results, we can see that we also have just a baseline data set, which doesn't have any synthetic imagery in it. And then we have our synthetic data set, which has the synthetic imagery that we generated from GPGAN added to it. And then we also have a previous BAS Connections team that also added synthetic imagery to a baseline data set, but their synthetic imagery was taken from a 3D CAD software called City Engine, which has different 3D infrastructure assets, including wind turbines. So they were able to have a 3D model of a wind turbine from an aerial view and then crop that out and copy and paste it into different areas. So that was their approach to the synthetic imagery. And we found that when looking at the average precision measures, our synthetic data set performed 9.7% better for the within domain experiment and 31.7% better for the cross domain experiment when compared to the baseline performance. And the cross domain is the real measure that we're looking at here. And when compared to the Cydia Engine synthetic data set, which is the one from a previous year, the within domain performance increased by 1.7% and the cross domain performance improved by 5.9%. And I'll let Frankie dive a little bit more into the conclusions and our next steps.
Yeah, so getting to the conclusions we got from that, we were very happy to see how well the model performed with our added data. It was there was a pretty clear trend that our synthetic data set was performing better in the object detection, not only from the baseline, which is the main goal, but is also performing slightly better than the other method of synthetic imagery that we have currently tried, which was that 3D CAD modeling that he was talking about. And so I think one of the big things to note here was that the performance of our synthetic data set improved in the cross-domain experiments by 31%. And that's huge here because the cross-domain experiments is what was kind of the goal of this project, in that, you know, there's all of this rich imagery and data of, let's say, you know, electrified nations in the West, like, you know, the United States. But if we're trying to kind of automate a mapping of energy infrastructure in like sub-Saharan Africa, where there's often, you know, gaps in energy access, then we're going to need to do these kind of cross-domain things where we train on, you know, imagery from the US and perform, you know, our testing on sub-Saharan Africa. And so being able to improve cross-domain performance by 31% is huge in that goal. That's exactly kind of the goal of a project. And it really helps, you know, bridge that gap in object detection performance. In terms of future work, there's definitely a lot that we can do to still improve that cross-domain performance and just kind of the overall performance and working towards our goal of automating this mapping of, you know, we have tons of satellite images, and then can the object detection model just automatically detect different energy infrastructures? Kind of one of the first obvious things would be, you know, we did our tests using wind turbines, but expanding that to using, you know, transmission towers, power plants, substations, et cetera, and just kind of validating that our methods are not only working for wind turbines, but also working for other energy infrastructures that may be less homogeneous in their appearance. Other future work things, maybe, you know, slightly tuning our models or our data generation process and seeing if we can tweak out any, or we can eke out any more improvement in terms of performance. There's also, you know, so we performed our tests using something called YOLO v3, which is an object detection model. And so potentially updating that to the newest version, which is YOLO v4, might be able to improve our overall performance in the different experiments, and would also be important for testing on, it would also be important to see if our synthetic data is still improving the baseline. And the other thing would be expanding from just the Eastern Midwest and Northeast domains and using the Northwest and Southwest domains, or just cross-validating there to see that our data set is improving these within domain and cross-domain experiments, regardless of what domains you're using. And so ultimately kind of our future work is divided into expanding this project out to different energy infrastructures, and kind of, just working to in different domains. And then the other is just trying to continue to improve object detection performance. So and that's kind of an overview from the poster of our project, but we are more than willing to answer any questions that you guys may have.
I guess to get us started a little bit here. So you first of all, great job, team. Great job. When you're looking at this comparison between the approach that creates these new synthetic data sets from real examples versus creating them from synthetic worlds, what do you think are the pros and cons of those two approaches in practice if your goal is to have better performance across domains?
Yeah, I can kind of take that. So using 3D models, it's definitely an easy approach in terms of being able to kind of place these on these different destination images. I'm sure it's a very quick solution. Potential downsides to it may be if it's synthetic as opposed to a real wind turbine, there might be slight differences in terms of its appearance, as well as also if we're just kind of placing it on the destination image, it might be contextually odd. For example, if you are placing a 3D model on water or in the middle of a city on town hall, it's going to look weird if there's just a windmill with a shadow just being placed there. And so our method of using real imagery, when we did that, we decided to keep some of the contextual information around the windmill. So not only is it real in terms of the windmill, there's the shadow, as well as a little bit of background around the image. And that allowed it to kind of blend it in with the background better. In these examples, it was able to turn a deserty windmill grassy. If I were to put one of these windmills on, say, water, it would kind of try to blend it and kind of make it green like grass or something like that. Like it would definitely perform better in terms of making it more realistic than the 3D model.
Appreciate the answer. Any other questions?
Jose here. First, congratulations. I am have been part of previous Fast Connections work, so I am really happy with the results you got here. I am a great fan of all the work that Wayne and Kyle produce on this subject area, and it has a huge impact not only within academic. I can tell you from experience that companies, not only in the US, but in all the geographies, are following his work for applications on industry. So any progress that you're making in this area, it's really appreciated, and it has value outside of academic area. Saying that, I hope I don't know how many of you are going to continue with the project, but if you do, try to devote as much time as you can, because from my experience, I think it's always possible to do better, but I wish I have devoted more time to reach better goals and get some more concrete results. So good job on this. I'm looking forward to future job here. Thank you.
Yeah, thank you so much.
Thank you.
We're all at least planning on probably in some regard to continue with this next year. And yeah, we definitely, I think one of the reasons that probably all of us joined was that we saw that not only are we going to be, applying these like new techniques of like deep learning or whatever, but that we are actually doing something that we were passionate about and that we feel like we're actually making some kind of concrete difference, whether it be now or in the future, we can definitely see that our work has kind of a noble cause. And so I definitely appreciate what you said.
That I will mention, Jose was in last year's Bass Connections team, and so a lot of the results that are being shown here are ones that he and the team put together. So glad, Jose, you could make it today as well.
I recognize him from the Vast Connections video.